Okay, so the next question that we got on the menu today is asking us a monoatomic ideal gas is held in a thermally insulated container with a volume of almost 10% of a cubic meter. The pressure of the gas is 115 kilopascals and its temperature is 325 Kelvin. What volume of the gas must be, or how much should we compress the gas to what volume until we get its pressure up to 185? And we're going to assume that the temperature is constant. And at what volume of gas will the temperature have? At what volume will the gas have a temperature of 279 Kelvin at 2 cubic meters? I think that might be the answer that they're giving us. But okay, let's do this question and let's figure out. Let's do the physics. So the key word that we want to see here is ideal gas, and as we all know, our ideal gas law. Let's write that out. Is PV equals nRT. Okay, P is going to be pressure. V is volume. N is number of moles. R is the Rydberg constant. And T is Kelvin. I mean, not Kelvin, is temperature in Kelvin. Okay, so what we know is that our P, our V, and our T are going to be variable. And let's do a different color like blue. And these are going to be constants. And how do we know that we're constant? Well, the Rydberg constant, it has to be a constant, but for the number of moles, it's in a thermally isolated container, and you can't be thermally isolated unless you are isolated in terms of volume as well. So like you can't be adding in new things into there. Okay, so let's isolate all the constants, and then with the variables, they should like match up with each other. Yeah, so first thing that we're going to want to do is isolate the constants. So we have just N and R, so we just have PV over T is equal to NR. And we're going to change these. So let's actually say we can have like pressure 1, volume 1, temperature 1 is equal to pressure 1, pressure 2, volume 2, and temperature 2. So temperature 2 can be like what we have finally, and the 1 values corresponds to what we have originally. So let's actually write out these values. So our first pressure, P1, that was given to us as 115 kilopascals. Kilopascals. Oops, I completely messed it up. Kilopascals. Our volume 1 is going to be 0.0930 meters cubed, and the temperature was 325 Kelvin. 25 Kelvin. Okay, now to what volume must the gas be compressed to increase its pressure to 185? Okay, so this will give us P2, 185 kilopascals. And we're going to assume that the temperature is going to be the same because it didn't say that we're going to change the temperature. So it seems that we're just reducing the volume to increase the pressure. Okay, so we're solving for the volume. So given this relationship here, let's solve for V2. So V2, we don't know that. So we want to solve for V2. And that will be P1 V1 over T1 multiplied by T2 over P2. Since T1 and T2 are equal, we can neutralize them out of the equation. Okay, so V2 is just going to be P1, so that's 115 kilopascals, multiplied by V1, that is 0.0930 meters cubed, divided by the second pressure, which is 185 kilopascals. All right, let's ask our handy dandy calculator to get the answer for us. 115 times 0.093 divided by 185. And that gives us a result of V2 is equal to 0.05781 meters cubed. And this makes sense because if we increase the pressure, that means we have to reduce the volume, and the volume is smaller than it was originally. So this is going to be our brand new volume value. Okay, so that will be our result here. Cool. And we got the same thing? Yes, we did. So that's awesome. And then our second question is asking us, what volume will the gas have a temperature of 279 Kelvin? We would kind of need to, let's assume that the pressure is going to stay the same. So for part 2, we want to find volume. Oh, I think this is kind of related to the first one, except we're not going to have T1 equal T2 anymore. Okay, so for problem 2, or instead of P2, I'll write Q2. So this is going to be the same relationship, except we're going to have T2 is not equal to T1. So T1 was 325, and T2 is 279. And everything else is going to be the same. So the V2 here is going to be the same, except we're going to uncancel these, the T1 and the T2 terms. So we're going to have V2 is equal to P1 V1 over P2 times T2 over T1. So let's call this V22 because it's like the V2 of the second volume corresponding to the second equation. Okay, so it's pretty much just the same as the previous. So let's just rewrite that. V22 is equal to 115 kilopascals multiplied by 0.0930 cubic meters, 185 kilopascals, multiplied by T2, which is 279 Kelvin, over 325 Kelvin. Okay, so we can just really take our previous answer. Yep, so we take our previous answer multiplied by 279 divided by 325. The result that I calculated was V22 is equal to 0.0496 cubic meters. Okay, so this would be the result for our question here. Sounds good. And we calculate the same thing, 496. Sounds awesome. So, yep, we kind of did need to come to the conclusion that our temperature was increasing between the changes from the initial to the final. I'm very confused as to why it has 2 cubic meters. Not really sure what that corresponds to, but it's important to sometimes you'll get information in a question that is not relevant. Okay, so the above solution is good. Would be better to show the process with part 2 where the two temperature values are incorporated. Cool.